Okay, so let's start. We have a field F with 4 elements, 0, 1, A, and B, and we want to show that A plus B equals 1. Now, your instinct may be, we can start by eliminating A and B, right? However, you get to A plus B equals 0, but you don't even know what 0 is. So how do we know that A plus B equals 1? We're gonna have to fill in both the multiplication and addition tables. Now, since 0 is the additive identity, we already have the 0 entries filled in, and anything times 0 is 0, so we have that filled in as well, and 1 being the multiplicative identity, we've already filled in those. So without further ado, we'll start by deducing that AB has to be 1. So we have AB equals 0, then either A is 0 or B is 0, which is impossible. Both are impossible. If AB equals A, then applying the multiplicative inverse of A, we'll get that B equals 1, which is impossible. And similarly, we can deduce that if AB equals B, then A has to be 1. And then we conclude that AB has to be 1. And we can fill in the multiplication tables as such. Now we claim that AA or A squared equals B. So if A squared equals 0, then A equals 0, which is impossible. If A squared equals 1, well, we just proved that 1 equals AB, so A squared equals AB, and then taking the multiplicative inverse of A, we'll get A equals B, which is impossible. If A squared equals A, then A has to be 1, which is impossible. Thus, A squared equals B. And by a very similar argument, by swapping A and B together, we can deduce that BB equals 8. So we'll fill in the multiplication table, and that's already complete. Now we want to fill in the addition table. So we claim that 1 plus A equals B. So we can easily rule out A and 1. Now we get to 1 plus A equals 0, right? Like in the beginning, we proved that AB equals 1, so we can substitute that into 1. And then use the distributivity property, and we'll get that A times B plus 1 equals to 0. But now if we multiply A inverse on both sides, we'll get that B plus 1 equals 0. But we assumed initially that 1 plus A equals 0, so that means 1 plus A equals B 1 plus B, which would imply that A equals B, which is impossible. Thus, we conclude that 1 plus A has to be B. And by similar arguments, 1 plus B has to be A. So we can fill in the addition table according to our findings. So now we claim that 1 plus 1 equals 0. We can easily rule out 1. Now 1 plus 1 equals A, then we just proved that A equals 1 plus B, so that implies, so we get 1 plus 1 equals 1 plus B, which implies that 1 equals B, which is impossible. Likewise, if 1 plus 1 equals B, then we get 1 plus A, which is impossible. 1 equals A, pardon me. So we conclude that 1 plus 1 has to be 0. And now we claim that a plus b, a is also 0. We can rule out the easy case, a plus a equals a plus a equals 1. Then we get that a plus a equals ab, which implies that one plus one equals b. But we just proved that 1 plus 1 equals 0, so this is impossible. And if a plus a equals b, then we get that a plus a equals 1 plus a, which implies a equals 1, which is impossible. Therefore, we conclude that a plus a must be 0. And by similar argument, conclude that b plus b is also 0. We can fill out the addition table accordingly. Now, finally, we can figure out what a plus b equals 0 implies. So if a plus b equals 0, then a plus b equals a plus a. You could use b plus b, but and the same thing would hold. But anyway, b equals a, which is impossible. Therefore, a plus b has to be 1. And we've completed the addition table. Now, if you notice carefully, this field with addition is actually called a Klein-Four group, which you may learn in upper year courses. But that is beyond the scope of Math 102. So I'm not asking you to check that.